the speaker, so please start.
Okay, so thank you very much. So in this talk, I want to report some advances that have been produced in different steps on Kadomtsev-Petviashvili hierarchies viewed in a generalized way. So for this, I will need to add some new material on to the algebraic setting that is in general used for this hierarchy. This new material remains in the setting on differentials. So since this is not so widely known topic, I will do some preliminaries in order to explain how it works, what is it for, and why it fits with our with the hierarchy. So it is the first part of this talk, where I start from very basics on diffeologies, and I construct diffeologies on the groups defined by Moulazé in order to construct the solution of the KP hierarchy. So with this setting, this adds, we can state some well-posedness. I will precise what I mean by well-posedness, and then I will analyze what we are used to find in the context of the KP hierarchy, that is the presence of the Sato operator and the Hamiltonian formalism. Then, from this generalized KP hierarchy, in the third part of the talk, I will try to explain why it seems important to generalize this hierarchy. So, first of all, diffeologies. So, diffeologies have been defined in the 80s in order to circumvent the lack of an atlas in some not so nice objects. So this is a way to deal with singularities, and this is also a way to deal with some infinite dimensional objects on which nobody can prove that there are charts, or it is known that we cannot give any system of charts. How does it work? We define, in fact, what are the smooth functions from an open subset of an Euclidean space to a set X. These smooth functions need to have some conditions which are natural for classical smooth maps, which ensure that differential geometry can be developed with these assumptions. So these assumptions are very natural. They, in this family of parametrizations that we call a diffeology, we need to have constant maps. We need to have a property of stability by reduction and by gluing. So this is very natural, and it needs we need also to fit with the classical composition of smooth functions from an open subset of an Euclidean space to another. So with this setting, there are many properties of differential geometry that can be proved. First of all, if we consider a map from a diffeological space to another, then it is called smooth if it sends smooth maps, smooth parametrizations to smooth parametrizations. With this, we can define a pullback diffeology, and we can define a diffeology on any finite or infinite product. So here comes the first example of interest. You know that when we try to consider an infinite product topology, then we have problems to define open domains of charts. Here, there is no problem with the differentiation and the smoothness of the maps. The same way, if we have a subset of a diffeological space, it is a diffeological space. We just pull back the diffeology of the full space to the subset. And with these two approaches, we can make a definition for smooth algebraic operations on diffeological space. So imagine diffeological monoids. So these are compositions, diffeological groups. The composition and the inverse map are smooth. Diffeological fields, rings, vector spaces, algebras. And what is interesting for me in this talk, it is differential algebras. So it is a diffeological algebra with operations that are smooth and with a derivation which is smooth too. Before going on, some examples. So any smooth manifold is a diffeological space. In any case, finite dimensional, infinite dimensional. The only point is that you need to have a locally convex topological vector space, which is modeling the manifold. In another way of thinking, you can find non-commutative torus, algebraic varieties. The algebraic varieties, these are only kernels of polynomials. So as a subset, they are diffeological spaces. In the same way of thinking, differieties, cellular complexes, groups of diffeomorphisms, and here we do not have to assume that we have an underlying smooth compact manifold. We can construct a diffeology on any group of diffeomorphisms for any diffeological space. So for example, for an infinite dimensional let's say Hilbert manifold, it's possible, and even more. And we can consider also spaces of functions which are not manifold. So for I took here the example of the Sobolev space H1 half of S1n, where n is itself a finite dimensional manifold. So here the low regularity of the functions do not allow one to define some charts on this space, but it has a nice differential geometry with the help of the diffeologies. So this example is actually published. It is why also I insist on this one. Let me just mention a class of examples. Why do I mention it? I mention it because there is a paper which is to be published on application of Fröhlicher spaces to diffeolities. And the second reason is that I was surprised to find a PhD thesis on the application of Fröhlicher spaces, which is very recent. So I highlight this fact. So now the diffeologies we will see what for. I start with differential diffeological algebra with unit. So on this algebra I can define the set of formal pseudo-differential operators. And well, here I make a little abuse of notation. I identify the formal differential operators with their symbol, but there is a nice identification, so I can do this approximation of vocabulary. And first of all, pseudo-differential operators are a subset of A power Z. So as an infinite product, it is a diffeological space. And on this infinite product, the splitting into differential part and integral part is just a splitting between components, so it is smooth. Then after we define addition and multiplication, and the point is that we have assumed that the differentiation is smooth in A. So the formulas are smooth too. So you see here that what is encoded in the diffeologies is that simply the coefficients of the pseudo-differential operators are smooth. That's all. Depends smoothly on some parameters. So in this concept of diffeological algebra, I have assumed that also the group of the unit that I note here A star is a diffeological group. That is not only the multiplication but also the inversion are smooth. Then with this assumption, I get a structure of diffeological unital associative algebra on PCDO of A. This is then one step. Let's go to another step, because now I need a countable family of time variables. So I set that the evaluation of the valuation of Tn is n, and I take the formal series in the countable family of variables. So now remember that again an infinite product has a product diffeology. So it is also the case for the formal series with coefficients in A. And the same way, we can check that the multiplication and the addition in the formal series are smooth. So, and the inversion too, of course. So I can form the diffeological differential algebra PCDO of A hat. And even more, I can form two algebras that are not in PCDO of A hat, but that are bigger. That are also I have put diffeological, so these are diffeological unital algebras. What for? The Moulazé groups. So I start with a group which is a group of let's say bounded operators, even if we are in formal operators, which is 1 plus the integral operators in A hat. This is a diffeological Lie group. So I need here to say that when I say diffeological Lie group, this means that we have also a bracket on the tangent space at the identity, which is not the case in any case. I will say more in a few minutes. And with this group, I can define also the groups psi hat star and d hat star. So these are the groups of the decomposition which is necessary to integrate the Kadomtsev-Petviashvili hierarchy. We have a decomposition into a big cross product, and the new point is that the decomposition is smooth. That is the map which sends U to S and Y is smooth. So now let me give you more details about this problem on Lie algebras. When I said that a diffeological group is a group for which multiplication and inverse are smooth. It is possible. It is always possible to define a tangent space, which is defined kinematically. You take smooth paths and you take germs. The germs of smooth paths passing at the identity form a diffeological vector space. But there is a problem for the adjoint action. There is a problem because this tangent space can be very big. For example, if you take R2, there is a diffeology for which this tangent space is with uncountable dimension. With this kind of problem, you can imagine that there can be some technical problems to show that the double tangent can be reduced and define a nice Lie bracket for vector fields. And this is exactly the key point. Vector fields are not well defined, and of course the bracket of vector fields is not well defined at all. And we have to assume some technical conditions to prove that this bracket of vector fields exists and is in the good tangent space. So when it happens, these diffeological groups are called diffeological Lie groups. We know that it may not happen, but it is so difficult to prove that it does not happen in an example that actually we do not have any proven example of diffeological group which is not a diffeological Lie group. I think that psi hat star is a good candidate because, let me go back, when you see the constraints on the valuation in T, then you will have series for alpha in Z, and a priori the bracket will not pass to this the Lie bracket will not pass to this full group, to this full vector space. Sorry. So this is only an intuitive indication, but this can be the first diffeological group that will prove that diffeological groups are not all diffeological Lie groups. So, since I have talked about tangent space and Lie algebras, and since I am in a seminar on geometry of differential equations, I have to mention another approach to define the Lie algebra of the group of units of some groups of PDOs, which is made algebraically by only assuming that there is an exponential map, and by looking at which formal symbols may match with the rules of the exponential map. So this is another way to define a Lie algebra, which is not the one that I consider here. So, in fact, in these groups, there are many ways to define tangent spaces. These are two. I know 3 others, and actually things have to be clarified because fields of applications are so wide that in fact we have to match with applications under considerations before making some generalities that are irrelevant. So this problem of tangent space is still a problem. Now, let us go to the KP hierarchy. So I take the classical framework, but now A is not C infinity of S1R, but just a differential algebra, and I take the series in A. And when we look at the algebraic construction of the solution, we start with an operator U, which has a well-defined formula in psi hat star, and we consider the decomposition, which allows to define S and Y to have the formula for L. So these are actually in the existing literature, these are only algebraic operations. But remember that now psi hat star is a diffeological group, and that the decomposition is smooth. This means that the operation is smooth. That is, it depends. It smoothly depends on L0. This is the statement of the well-posedness. So well-posedness means smooth dependence. And let us go a little bit further on the analysis of the situation, because around the KP hierarchy there are many things that have been developed, and some of them appear as non-necessary. For example, when in the classical context, we assume that L0 is expressed with the help of a Sato operator. This condition cannot be fulfilled for any L0. There is a condition for the first non-trivial coefficient, the coefficient of order -1, which is not always fulfilled, and this condition, when we analyze the proof via R matrices, this condition is not necessary. And the second point is that the Sato operator is not unique. We have to consider also commuting operators which can modify it. So for these two reasons, it is a good point from the viewpoint of the KP hierarchy without considering any other subject. It is a good point to consider this Sato operator as non-necessary. And now, if you say that A is any differential diffeological algebra, then the condition of existence of S0 can be a problem which can be even more difficult. So here again, I think that we can be happy that this operator is not needed, even if it has some nice properties and some nice applications. Second point, the KP hierarchy is related to a Hamiltonian formulation, and Actually, the Hamiltonian formulation is related to the presence of a good trace on pseudo-differential operators. So when you try to generalize from the infinity of S1R to any algebra under consideration, then such a trace may not exist. This is also the case for the infinity of R, when you change S1 into R. So the point is that we can ask what is really relevant for this setting, what is really necessary, and it appears that some kind of generalization of the Hamiltonian formulation may be interesting to state, because a classical one would be impossible. So this is a work which is in progress, a work in, let's say, a nice generality. But we already have a toy example where such a generalized trace can be constructed. So the example is just formal series in Z with coefficients in infinity of S1R. Then the Adler residue extends very trivially to this setting, and it is with value in a series with coefficients in R. So we get a generalized R of Z valued pairing and generalized Hamiltonian functions. But very fortunately, this generalized setting enables one to get back the generalized KP hierarchy for this differential algebra. So let us go to let us descend now to the equations of the hierarchy. So in order to get back the KP equation, the classical way is to consider the zero curvature equation. So I stated it in its full generality, but of course, when you take K and L very large, actually, I think that no one is able to state the equations that are consequence of this equation. But it is possible to prove the Zakharov-Shabat equation from the KP hierarchy, even for a general algebra. So here let us just analyze what happens for the lower terms. For this, I will use notations for the coefficients, for the first coefficients of the solution L, and as in the standard case, the equations with T1 just give d over dt1 equals to partial, the differential. And since this is not d over dx, integrate like this, and we have only a formal integration. Well, we can remark that it is well posed, and that the operator exp of T1D is in psi hat star. But anyway, it does not furnish so much things more. Let us go now to the T2, T3 variable. So this is the classical way to get the KP equations, and we can deduce a system. So this system is the strict traduction of the T2, T3 equation in the coefficients. So these are the conditions for that ensure that the T2, T3 ZS equation is fulfilled. There is no simplification here. In this general case, you see that we have some terms that are not present in the classical case. But what we can first state is that the KP hierarchy produces the solution of 3. I say the solution because of what I said before. This is exactly the Zakharov-Shaba condition, and of course we can state well-posedness, that is smooth dependence on the initial conditions u minus 1 of 0 and u minus 2 of 0. Then let us just precise few things about the classical setting. When we have A equals C infinity of S1R, then we can deduce from this system the KP2 equation. So when you look at this equation, it is an evolution equation in T, and the initial conditions depend on the variable X and Y, while the KP hierarchy is defined on functions in the variable X, which means that when you consider the variable Y, you have you define u of y from u of x. This means that the KP hierarchy furnishes only solutions for a restricted class of initial values for the KP2 equation, and a restricted class, so for the KP2, a restricted class of solution for the KP2 equation. Now, let us go back to our generalized setting. I try to define, to show you some examples of equations which were surprising to us to find. And I think that the most surprising is the first one that I show you. Here, I take C infinity of Rn into Rn, viewed as vector fields over Rn. And I take the gradient as a derivation. Then the operations on Rn are just under the coordinates. That is, these are only multiplication and addition, only on from the same coordinate to the same coordinate, u1 with u1, u2 with u2, and so on. So with this setting, we get a family of equations, which we get in fact 4 equations, and we need to transform them a little bit. But a consequence of the system that we got before is that we get an equation which looks like Navier-Stokes, but we did not manage to find a way to deduce also that the divergence is 0. So it is not a Navier-Stokes equation, but if we add the constraint of divergence-free solutions, then we get Navier-Stokes. Another example comes from a very different setting. When we consider CDO of S1R, it is possible to embed it into another class of formal pseudo-differential operators, which is also a class which is used in the literature. That is, it is a class where to CDO of S1R we add the sign of the Dirac operator, which has a symbol which is not in CDO. You see, it is Xi over absolute value of Xi. So it is for Xi positive it is 1, for Xi negative it is -1. And with this added symbol, we can show that we have an integrable almost complex structure, and we get an extended setting for pseudo-differential operators for the KP hierarchy. So we have described this hierarchy algebraically, I would say, in full details, even if we can make more details, but we have given many details, but we did not give the corresponding equation. So it was a remark received from 3 different people that the KP equation was missing, and it would be interesting to state it. So it is a formulation under progress. Of course, we have it, but it seems to give some let's say funny properties. So we keep this subject again, let's say, for a little time more, in order to be sure that we do not miss anything. Then I have given 2 commutative Bayes algebras. Let's go to non-commutative ones, because remember, just let me go back. We have a bracket here, and it seems that there may happen some things that are not present in the classical case. So how does it work? In fact, the case of a non-commutative algebra has already been discussed when we consider smooth functions into the field of Hamiltonians, the equations are stated, and they give non-linear equations, but with our work we can state now well-posedness again. If you consider non-commutative algebra, but a derivation which is an exterior derivation, that is d square equal to 0, then we have, let's say, a simplification, even if the equation is not so simple, with a bracket. So here we did not investigate for the moment the case of a graded differentiation, because there are technical problems, of course, but it is under progress, and we hope that we will be able to furnish some results in this new setting in let's say some time, and with strong applications. Another example. Consider an algebra which is obtained by deformation with a Moyal product. Then the corresponding KP equation has already been stated, and we recover the KP equation which already exists. Again, we have well-posedness. And let me finish this page with an example. Well, I feel that it was like a challenge between me and the other collaborators. If we take an algebra of pseudo-differential operators. For simplicity, we assume that these are only formal series in R. And if we take the derivative, which is called the Pincherle derivative, it is an inner derivation in R of X. It is a derivation on A. And we have a system which looks like the system 3, of course, but just have a look at what happens here. U minus 1 and U minus 2 are pseudo-differential operators, which means that they have an infinite number of coefficients, so that each equation gives an infinite number of equations in R of X, and these equations have to be first stated and investigated. The second line will give us nonlinear equations, which are, of course, integrable, since the KP hierarchy is integrable. But well, it has to be stated. So this last example was to stimulate the audience, let's say, by open questions, and I will turn to open questions now. Open questions that are in progress and in very big progress is the application to differentials. So there is actually a proceeding paper which has been accepted a few days ago, and we have a more complete study on the elementary difficulty, so on a difficulty on jets, and with respect to a differential or to a true PD partial differential equation, and so on. So I was hoping that it would be pre-published for this talk. Unfortunately, we have some cosmetic changes to do, but it will be available online, let's say, in few days. So it is why I have put November the 23rd plus epsilon. Another perspective, it is, of course, the full study of the generalized equations that I have given in my talk, or generalized equations that are not given in my talk, but given in the papers. So generalized setting, we can imagine many things. The imagination is very rich to generalize everything. So it is a very open field of investigation, which has some promising examples. Another perspective is the Kadomtsev-Petviashvili hierarchy for non-formal pseudo-differential operators. So this is another way of thinking, not from the viewpoint of classical integrable systems, which involve PCDOs as I define them in this talk. These are non-formal pseudo-differential operators. These are true operators acting on smooth functions. And it is a natural question because we can derive PCDOs from non-formal pseudo-differential operators. So there are some investigations in progress. There is actually a preprint which is available on arXiv with Enrique Reyes, which describes how the action of orientation preserving diffeomorphisms of a circle act on non-formal Sato operators, and how it is related to a non-formal KP hierarchy, which is proven to be well posed. But it is only a first step, because we think that we have more interesting results and unexpected correspondences in this direction. And of course, more things that I cannot say because they are in let's say too early stage of development. So I have now to thank you for your attention. I am sorry for the video which was not working, but as you all have understood, I had many problems in launching and so on. So I am anyway happy to be here and to have be able to give this talk to this audience. Thank you very much.
Thank you for the talk. And are there any questions or remarks?
May I say a few words?
Of course.
Yes, because sometimes, especially for people who are doing differential equations, they have a natural doubts about the why people consider generalized generalizations and some non-commutative generalization or some strange coefficient equation generalization. They are non-physical, they are non-interesting, and so on and so far. But few recent counterexamples shows that it is not completely true, and it is worth to study or as much as possible generalizations of classical, say, classical equations, which looks physically non-interesting. In fact, I will not speak about very famous story about Penlevé non-commutative Penlevé equations, which we studied with Volodya Retach. And then after a few months, when our preprint is absolutely toy model for all Penlevé people, they said, it's toy model, you have non-commutative time. What does it mean non-commutative time? And just a couple of months after our preprint appeared in the archive, two mathematicians published a paper when the same equation was a result of very, very physically motivated model from some integrable field theory of Slavnov-Karepin. And I will not go into details. I just will speak about the examples of Jean-Pierre today. When we discussed these generalizations, we also have some doubts how much it is interesting for other people. And last week, I attended a seminar, and in this seminar, a young Brazilian mathematician told about his paper with Prokhorov and another Brazilian mathematicians, and they considered very, very interesting physically motivated models which goes in random field descriptions. And as a result, they obtained two coupled matrix KdV equations, which are exactly correspond to what Jean-Pierre today told. So matrix PDV KP equations, which contains this matrix KdV, they are also obtained, and it is very, very interesting. They didn't know that such non-commutative equations mathematicians studied before, so I gave them these examples, and it is exactly up to coefficients correspond to our non-commutative KP hierarchy equation with T2 and T3. That's what I want to say.
Yes, may I add some remarks or opinion on this subject?
Yes.
In fact, the KP hierarchy is technically interesting from a spectral viewpoint in the classical setting. That is, we produce some families that describe more or less, or that decompose many other situations of interest. And I guess that these properties are, in fact, the deep reasons why in generalized setting we will get also some interesting examples. It is just for the moment it is only an intuition, but I have read many times that the KP hierarchy stands like a universal hierarchy. Well, it is almost true because there are more universal, of course, but it carries it really carries some differential properties which are intrinsically related to the underlying algebra that we consider. So once we have an algebra which is of interest, the KP hierarchy, to my opinion, will be of interest, and it will produce some things that may appear strange or unexpected, but maybe trivial sometimes, but it is a direction that does not have to be neglected.
Okay, thank you. More questions, remarks? Okay, so thanks again for nice talk. And next week we will have the same time